Hi, I'm going to share my screen of the poster. So, hello everybody. My name is Miguel Serrano Romero, and I'm a PhD candidate in nanoscience and nanotechnology doctorate program at Simvestab Zacatenco. It is a pleasure to present my poster entitled Large-Scale Production of 2D Nanomaterials Using a Green Method for the Development of PVDF-based Piezoelectric Nanocomposites by 3D Printing, as part of the Material Research International Material Research Congress, Cancun, Mexico, 2025. This work was carried out in collaboration with Dr. Prokhorov, Dr. Luna Bárcenas, Dr. Santoyo Salazar, Dr. Baena Uribe, Professor Martínez Hernández, and Dr. Velasco Santos. As background and motivation, piezoelectric materials are gaining significant attention due to their potential in energy harvesting and sensing devices. Among them, PVDF, which is polyvinylidene fluoride, is a lightweight, flexible polymer with excellent piezoelectric properties if we have specific phases or structure, crystalline structure. Incorporating 2D materials such as molybdenum disulfide or graphitic material can further enhance PVDF's electrical, structural, and mechanical performance. Molybdenum disulfide is a layered semiconductor with unique optical and electronic properties, making it a strong candidate for improving the performance of piezoelectric nanocomposites as polyvinylidene fluoride. However, one of the main challenges is producing these nanocomposites in a scalable and sustainable way, suitable for additive manufacturing processes like 3D printing. So the research gap and aim in this project is that current studies often focus on a small scale laboratory synthesis without fully addressing the preparation of base materials for filament extraction for 3D printing. So our work focuses on establishing the groundwork of producing PVDF and molybdenum disulfide piezoelectric nanocomposites in filament form, starting with the preparation and characterization of these base materials. So we know as an introduction that we already know in different groups of researchers how to obtain different materials for specific areas like materials, nanomaterials, medicine nanomaterials, agriculture, electronics, robotics, environment. We know how to synthesize different materials in this scale. But the focus on this group and this investigation is to have a sustainable impact to obtain a large scale production, which increase the availability, lower the cost, eco-friendly production, and also the reduction of waste. And finally, we are trying to gain an eco-friendly production, which creates a value model that integrates the environmental, social, and economic areas. So to obtain our molybdenum disulfide nanomaterial and nanosheets, and then integrate it with PVDF, polyvinylidene fluoride. So the objectives of this study were, first of all, to characterize the PVDF in different physical forms for extraction sustainability. Secondly, to exfoliate the molybdenum disulfide using a green scalable method developed in our laboratory, which is a two-step method of exfoliating the material, the precursor material. And in third stage, we want to analyze the structural, morphological, and optical properties of the prepared materials, focusing on the semiconductor-based energy harvesting applications. So as methodology, as we see in our poster, we have a two-step methodology to obtaining the exfoliated molybdenum disulfide. First, PVDF was obtained in powder and pellet forms and characterized to assess crystallinity, thermal stability, and morphology. Secondly, for the molybdenum disulfide, we applied a two-step process that separates bulk material of molybdenum disulfide in different layers. We, as a goal or aim, we want to obtain monolayers of molybdenum disulfide to work with nanosheets as the precursors of the nanocomposites of PVDF and molybdenum disulfide. So in this two-step process, we have as a first step the steam blast, which is a steam explosion, a rapid expansion process that separates the bulk material of molybdenum disulfide in different layers. And the second step in the first stage is to apply an ultrasonic exfoliation, which is high frequency ultrasound waves, further to separate and reduce the molybdenum disulfide into nanosheets. So the exfoliated molybdenum disulfide was then washed, dried, and characterized using XRD, X-ray diffraction. Also, we want to apply SEM and TEM microscopy, and also Raman, we did Raman spectroscopy and UV-Vis spectroscopy. This method enables large-scale production of semiconductor-grade molybdenum disulfide, layered molybdenum disulfide with minimal environmental impact. The second stage is to incorporate the PVDF and the molybdenum disulfide to obtain the nanocomposites as an extruded filament, and finally to print this material in non-conventional forms. So as results and characterization for PVDF, which is the first part, we did X-ray diffraction and also Raman spectroscopy to see in which structure or phase we were working with the material, precursor material. So for PVDF, X-ray diffraction confirmed the presence of alpha phase or alpha structure, which is an stable phase of the material of the PVDF, which has no piezoelectric properties. So we need to improve this beta phase or gamma phase or different phases as the alpha phase to induce the presence of piezoelectric properties of the PVDF, which is the first part of this analyze and characterization diagrams. So we have confirmed the presence of alpha phase, which is or which has not piezoelectric properties, but we know with different research groups or articles that we can induce the beta or gamma phases with the incorporation of molybdenum disulfide. So we want to incorporate our molybdenum disulfide already exfoliated with our two-step process, and with this incorporation we could have improved and enhanced the piezoelectric properties of the PVDF. So for molybdenum disulfide, XRD patterns confirm the hexagonal phase of the material. We have both exploded with the steam explosion process and the exploded with the steam explosion process, and then exfoliated with ultrasonic exfoliation. So we have these two ways of preparing our material, and we already see that we have our predominant phases of molybdenum disulfide. So also applying the exploded and exfoliation process, we already have a non-contaminated contaminated molybdenum disulfide. So we have molybdenum disulfide, and we have the hexagonal phase with peak broadening indicating reduced layer thickness. Also for molybdenum disulfide, Raman spectra showed the expected E2G and A2G bands of the modes of the material shifted in a way consistent with few layer structures. So we can see the bulk material, the exploded molybdenum disulfide, and then the exploded and exfoliated molybdenum disulfide, and how the increasing of the A1G mode and the prevalence of the E2G mode, which is associated to these vibrations out of plane and in plane vibrations. So we need to apply TEM and SEM microscopy to confirm the nanosheets morphology, but we already applied or did the UV-Vis absorption, which revealed the band gap expected for high quality semiconductors molybdenum disulfide. We have the bulk material, which has an indirect gap of 1.2276 for bulk material, and a direct gap of 2.1388, and for the exploded molybdenum disulfide, and a direct gap of 2.27 for the exploded and then exfoliated molybdenum disulfide. We can assume, because of different investigations, that bulk material has, as we see, the 1.2 electron volts, and in different layers, in this case monolayers, but in our case, the material that we have already synthesized or prepared, we have a different or an increase in the band gap of the material. So combining PVDF with semiconductor-grade molybdenum disulfides opens the door to flexible, high-performance piezoelectric nanocomposites by preparing and characterizing the base materials in this way. We enable the extrusion into filaments for 3D printing as in the second stage of the investigation and the research that we are presenting in this poster. And this approach paves the way for sustainable large-scale manufacturing of devices such as contact sensors and self-powered electronics. As future work, we will incorporate the molybdenum disulfide into PVDF matrices for homogeneous nanocomposites, extrude this into filaments optimized for 3D printing, and evaluate the piezoelectric performance under mechanical stress, and finally assess stability and durability in real applications. As conclusions, we have demonstrated a scalable green method for producing semiconductor-grade molybdenum disulfide and characterized PVDF in multiple forms, as we present in the results, in preliminary results. These results establish a solid foundation in the fabrication of PVDF and molybdenum disulfide piezoelectric nanocomposite filaments, contributing to the field of semiconductor materials for sustainable energy harvesting. I would like to thank my colleagues, advisors, and the institution for their support. Thank you for your attention, and I will be happy to take any questions. Thanks.